Go ahead.
Hello, welcome in 3CL4. This is lab 2. This video is introduction to the lab. First, I'll try to explain some simple experiments about control. Then we'll go through the lab PDF and the hardware requirements. Assume this is black block of the motor. This is the motor we have. And we know from the lab 1 that this motor has an output which represents angle. So this angle is represented by volt from negative 10 volt to 10 volt. This depends on the angle, whether it's 1 rev or 2 rev. So this represents either from 0 to 360 degrees or to 720 degrees. So whenever I say angle or volt, it is the same because the volt is the representative of the angle. So now if I want this motor to get to a specific angle or a specific volt, what should I do? I should give this motor an input signal so that this motor reach the angle that is required. One from the very simplest way of control is to make an input like this. V target minus this, let's say this is V out, minus V out. Why is this working? Imagine that our target voltage is 5 volt and now we are in 0 volt. So what will happen? We have V target 5 volt, we have the current volt equals 0 volt, so this is 5. So this volt pushes the motor in the direction that increases this volt. So we push the motor forward so that this volt increase. So what will happen? The motor will move with a speed that is proportional to 5 volt. Now the volt here is, instead of 0, it's becoming 1 or 2. What will happen? When it comes 2, so it's now 5 minus 2, it's what? It's 3 volt. So the motor is being pushed again, but with smaller volt. Toward what? Towards the angle we want. What will happen if this angle is exactly the same angle? So we have 5 minus 5. What is this? This is 0. So the motor will not revolve at all. If the motor speed was too high, so that the inertia makes the motors moves past the 5 volt. Let's say it went to 6 volt. So it's 5 minus 6, it's negative 1. So we force the motor to get back to the position we want. So we have this 5 volt. If we are below this 5 volt, we push the motor towards the 5 volt. If we are after this 5 volt, we push it back. So with this very simple control circuit, we can force the motor to settle on the angle we want or the volt we want. How to implement this circuit? It's a very simple circuit. You know from electronics, a summing amplifier, right? So we can have a summing amplifier with negative feedback, so it's something like this. It is positive, this is the output. We have one resistance here with V target, another resistance with V naught, and this is the feedback resistance. If all resistances are the same, so this is R, so the V out here equal to V naught plus V target. But the problem is because this is connected to the negative input of the op-amp, so we have a negative sign. So we have this negative sign. Okay, so the output here, so let's say this V output. So the output of the op-amp is the negative of V naught and V target. If we look here, we want negative V naught. So negative V naught is okay. But the problem is that the V target is with negative sign. But V target here is a positive sign. So what would you do? Invert it. So before we input V target here, we put an inverter here. So V target first is inverted, so it is negative V target here. So this is V target. Goes through inverter, so it's negative V target. When they are summed up by this negative summing amplifier, so negative V target, so it is positive V target, and V naught with a negative sign. So this simple inverter and summing amplifier works like this equation. This equation is simple as I said it, so it's just the difference between what I want and what is the output right now. This is very simple, and actually the next lab we'll be speaking about having the same equation, but instead of having this multiplied by 1, we can multiply it in general by a k factor. The same logic applies, right? Because whenever v naught is lower than v target, we have a positive input. Whenever v naught bigger than v target, we have a negative input. But now it's multiplied by some scale that is like amplifiers or decreases the volt going to the motor. If k is very high, so this will make the motor having like much more volt as an input. So perhaps this will increase the overshoot. If this k is low, it will decrease the overshoot. That's what we'll see in lab 3. But in lab 2, we'll keep this as simple. So we have this V target minus V naught. To implement it, we use a sampling amplifier. We have this negative sign, so we solve it by the inverter. How to implement an inverter? It's very simple. Another op-amp with also ratio R1, R1. So this is V target here. Since this is R1 and this is R1 and this is the negative feedback of this is the negative input of the operational amplifier, the V out is the negative of V target. This is from electronic circuits. So this is simple inverter, simple amplifier. We now have our first control system. Now we'll go to the PDF and try to make this hardware works. Okay. Now what is required in lab 2? As I said in the introduction labs, are required 3 parts for every lab. Pre-lab report, so it's like all the derivations and the equations you need for the lab. Second part of the lab, it's something that requires the hardware of the lab, and we have some kind of demonstrations. And the third part is the writing exercise. So the first part in lab 2, we'll have like section 1. So this is some discussion of the motor and some derivations and the questions. And the second question is the closed loop system identification. In this part, you get the equations and the derivations that will help us specify what is the constants for the motor. Okay, let's go for the hardware part. So we have this first part. This is the summing amplifier. This is the output voltage. This is summing amplifier, but we use here R1 equal R2 so that we have the ratio 1 to 1 we said in this lab. And this is the inverter amplifier. So we have R1 and R1 here. So for this one, V output is the negative of V input. For this one, V output is the negative of V input 1 and negative V input 2. Let's put this together. So we have this summing amplifier, the inverter, and this is the motor unit. So let's focus for a moment. What is the input? What is the output? What is the feedback? What do I want to control? The volt, right? So the output volt is the feedback. Where is my input? Where is my target? This is the signal I generate from the function generator. So my target volt is what I generate from the function generator. I pass it through the circuit, goes to the motor, and the motor gives me his angle output. According to this angle output, I control the motor. So my control signal goes to the command input of the motor. In the PDF, it will ask you to do some parameter to like adjust some parameters in the oscilloscope and function generator. Simply, first of all, we'll have like frequency of 100 millihertz here, amplitude of 6 volt peak to peak. It is a square wave. So we will require that the volt become positive 3 volt, then negative 3 volt, positive 3, negative 3 alternatively. For the oscilloscope, we'll press mean delayed and choose the roll mode for the display so that the display is continuous. You can open the quick measure so that you can get the peak-to-peak outage, the peak-to-peak amplitude. Okay, so this is the circuit that we have now. the circuit consists of, okay, so we have two operational amplifier modules. The first one has one resistance here, one resistor here. So this is the inverter. The inverter has the input from the function generator. So this is my input. My input goes to the inverter. We have the output here inverted. The feedback is coming from what? The feedback coming from the angle output. This is what I want to control, the angle output. So it is coming as a feedback. The inverted signal and the feedback are summed together to form my control signal that is going to the command input. So if the input signal and the angle output are the same, the difference is 0. So I ask the motor to do nothing. If the angle is higher, so the command input will have a negative value. So this will make the motor moves in the opposite direction. If the angle is lower than the target, so it will have a positive value here that will ask the motor to move in the positive direction. So that it always asks the motor to go to the right direction we want. So we turn this on and make sure that this is on compute, because there is a reset and hold. So when this is on compute, so this block is working. If you look at the motor here, it's turn and settles at a point. Turn and settle at a point. Turn and settle at a point. At what rate? At the same rate that we mentioned in the frequency of the square wave. So I ask him to go to some certain volt or angle. It tries to go there. It oscillates a little bit and then stands on the volt I require. Don't miss to connect all the grounds of this control unit with the operational amplifier to the function generator and to the oscilloscope. All the grounds here are connected together, so connect it like anywhere you want. So I put this in this ground, I put this in this ground, I put this in this ground. All grounds here are connected. But don't miss to connect the grounds. So this is the first part of the experiment. We have this like negative feedback, we have this like simple proportional control of a constant of 1. So if we look here at the output, we have, this is the angle output. So the angle of the motor was like resting in this position, and then you ask it to go for the positive one. So what happened? It goes very fast, so that's overshoot, then goes back in the negative direction, go positive, negative, till it settles on the required volt. And so on, and so on. This is 2 volt per division, so this is the one is the 3 volt. Remember that the volt here is 6 volt peak to peak, so we have 3 up and 3 down. So the angle actually rests in the positions that we want. So we input a 6 volt peak to peak, and the angle ends like 6 volt peak to peak. The amount of overshoot here depends on the constant of proportionality. We just make k equal 1 here, and we have around 40% overshoot. This is the first part of the experiment. You should do the same hardware and show me this oscilloscope output, and you should have this 40% overshoot as well. The second part of the experiment depends on an input sinusoidal wave instead of square wave. So we have the same frequency, 100 millihertz, and the same amplitude, 6 volt peak. But now we will go for a sinusoidal wave. Using this experiment, we will find the 2 constants of the motor, A and tau m. A and tau m are specific for each motor. So whenever you get A and tau m for this motor, this is our A tau m for this motor only. So 2 points to be mentioned here. First of all, if you did lab 2 on this station, you should do lab 3, 4, 5 on the same station here, because the values you get for A and 2 are specific only for this motor. They are characterized for this motor only. If you made like your experiment for A and tau m here and you went anywhere else, there is differences between A and tau m for every single motor. So first of all, the station you work on for lab 2 is the same station for the rest of the labs. Second point, you should keep the values of A and tau m with you, because you will need them in lab 3 and 4 and 5. If you didn't have this value with you, you will like do lab 2 again to get this A and tau m, and this is boring. So don't do it. So keep the values of A and tau m with you, and make sure that you work on the same station all the year. Okay, let's back to get to our experiment. So we have 6 volt peak peak sinusoidal wave with frequency 100 millihertz. If we look at the oscilloscope, the angle now it's not sinusoidal. Why is that? Because the motor in the case of very low frequencies is not linear anymore. The linearity of the motor depends on the frequency. If the frequency is too low, the motor is not linear. Now let's increase the frequency. Two things will happen. First of all, the non-linearity will decrease. Second of all, the amplitude of the signal depends on the frequency here. You will need to record what is the values of the maximum frequency and what is the value of the maximum amplitude. If you have both values, you can calculate the constants A and tau m for your motor. So let's start to increase the frequency. If we keep looking here, we'll find that the sinusoidal is becoming smooth and smooth as we increase the frequency. So we can open quick measure so that we can get like the peak-to-peak voltage. If we keep looking here, the peak-to-peak voltage is increasing. So we have this non-linearity, it's becoming linear now, and it's increasing. The peak voltage is still increasing, it's 9.8 now. So we went already past the maximum area. Now it's 9.5, 9.3, it's 8765. So what will happen, we have like starting with a small amplitude, we end with a small amplitude, the maximum amplitude somewhere in between. We started with 100 millihertz, we ended with 3 hertz. The maximum amplitude should be something in between. When you get the maximum amplitude and you get the maximum frequency, you can find the motor constants A and tau m, and this by this the hardware part of this section of this lab is done. So let's summarize what we're gonna do in this lab. So this lab consists of 3 parts. Pre-lab, you should do it at home, and so that you can get ready with your equations that you'll need to apply here the hardware and find A and tau m. Second part, the hardware parts. We have 2 parts. The square wave part, and we have seen it, and it's this 40% overshoot. The second part, this is the sinusoidal part, where you get the maximum amplitude and frequency. The third part is the writing exercise. The writing exercises are always open-ended. I ask you a question, try to write something that is logical. There is no constraints, just write 1 page maximum of something that is logical, that is replied to this writing exercise. The motor we are using is in negative feedback mode. We have this input of V target minus V out. Don't miss to connect the grounds. Please don't change the stations, and please have your A and tau m values for all the year. After you finish the lab, after you finish the writing exercise, please turn everything off and return everything as it is. Don't miss that everything has, so return this off, return this off, return this off, return this off, off. Remove all the resistors and connectors and get them back to the boxes. Okay, in some cases, perhaps not in lab 2, but some cases in lab 3 or lab 4, because of the excessive use of these control units by all signals, some cases that one operational amplifier is not working. So for example, you connected the circuit, you think that everything is fine, but it's not working. What you can try to do is, like, instead of using this operational amplifier, you can try another one. Because sometimes it happens, because of the excessive use, some operational amplifier didn't work for a while. So if that happened and you change the, like, instead of using this operational amplifier, use another one and it worked, please tell me that there is some operational amplifier that is not functioning here, okay? This will not be so common, but it can happen, okay? So that's for it for lab 2, and thank you.